about how to analyze the rigid jointed frame by slope deflection method. So first we have to understand what is sway and what is non-sway. So here one end is fixed, another end is hinged. If you apply the lateral load, this column will move like this. This lateral movement and lateral displacement of column is called lateral displacement of this column is called as sway. So first we have to understand what is the reason for sway. Reason for side sway. Here the boundary conditions both are same, but the load is acting eccentrically. So about this vertical axis, the load is not symmetrical. So this type of frame subjected to sway. It will undergo sway. So next one, the height of the column is different. For example, this is 2 meter, this is 3 meter. So but the load is acting at the center of the beam. So here the unsymmetrical above the height of the column. So this type of frame also will undergo sway. That is unsymmetrical shape. Unsymmetrical shape. So here unsymmetrical loading. Unsymmetrical loading. Third one is different end condition. So one end is fixed, another end is hinged. Hinged or roller. Okay. So about this vertical axis, these boundary conditions are different. So this type of frame will undergo sway. So different end condition. Different end conditions. So next one, non-uniform section of the member. So here the loading also symmetrical. If we divide into two equal parts, the loading also symmetrical. Boundary condition also symmetrical about this vertical axis, but the moment of inertia, the uniform of cross section is different. For example, this is 2I, this is I, this is I. So here we are having different cross section. So this type of frame will undergo sway. So non-uniform cross section. Non-uniform cross section. Non-uniform cross section. So another reason for sway is, so see here the boundary condition also same and loading also same about the vertical axis. If you apply the lateral load, so this frame will undergo sway. This is delta and this delta. The magnitude of this both delta will be equal if you apply the lateral load or horizontal load. So this is also one of the reason for sway. Another one is settlement of support. So these are all the reason for sway. These are all the reason for the sway. The first one is unsymmetrical loading. The first one is unsymmetrical loading and second one is unsymmetrical shape of the cross section and third one is unsymmetrical boundary condition and fourth one is non-uniform cross section and last one is horizontal loading. If any horizontal load act on the rigid jointed frame, it will undergo sway. So these are all the reason for sway. If the frame is subjected to sway, the total number of unknown is 3. So here this is on rigid jointed frame because this is rigid joint, this is rigid joint. After applying the load also the angle between the joint will not change. So that's why it is called as a rigid jointed frame. So here the load is UDL, symmetrical about the vertical axis and boundary condition also symmetrical about the vertical axis. If you apply the horizontal load, it will undergo some sway. So now the degree of freedom, we have to find out the degree of freedom. What do you mean by degree of freedom? Means independent translation and rotation that exist in the structure. So always the fixed and the degree of freedom is 0. Here also the degree of freedom is 0. here at the joint, for example, this is A, B, C, then D. So here theta B rotation is possible and theta C rotation is possible. Okay. So this rigid jointed frame is subjected to sway. Subjected to sway. So one more degree of freedom is this delta. One more degree of freedom is this delta. So now the total number of unknown is theta B, theta C, then delta. So we have to find out these three unknowns using slope deflection method. So for finding these unknowns, we can write the joint equilibrium equation because equilibrium equation is needed to find out these unknowns. So joint equilibrium equation we can write at B. Okay, the one is at B, another one is at C. So these both are joint equilibrium equation. Joint equilibrium equation. But our unknown is 3. But we are having 2 equation. Using this 2 joint equilibrium equation, we can frame 2 simultaneous equation only. But our unknown is 3. For finding third unknown, we need one more equation. That equation is called as shear equation. Shear equation. Along with this joint equilibrium equation, we can find out the theta B, theta C and delta. So here unknown also 3. Here equation also 3. One is at B, summation of moment at B equal to 0, summation of moment at C equal to 0 and shear equation. So now we will see how to formulate the shear equation. Case 1. The vertical line, the height of the vertical line is different. So it will undergo sway and horizontal load also acting here. So here P, the load is acting at the center of the beam, W. So the name here A, B, C, then D. This height is H. The overall height is H1. So here the UDL load is acting W per unit length. W per unit length. This height is H2. Okay. Now we have to use sum of all horizontal force equal to 0. So first we have to draw the free body diagram. So this is for the column AB. Column A, B. No need to consider this vertical reaction because we have to take the moment about point B. If you take the moment about point B, so the force into perpendicular distance, here there is no perpendicular distance. If we use also, we can get 0 value only. Okay. So the fixed end has 3 support reaction. One is this one, and that is HA, horizontal reaction. Another one is moment, that is MAB. So the name of this moment is MAB, which means moment at A along the member AB. Moment at A along the member AB. So here also one moment is there, that is MBA, moment at point B along the member BA. This is the member BA. Another one is this one HD. Okay, because this joint is the rigid joint. So the height is H1. The load is acting here P. So this height is H. So this is the free body diagram of the member AB. Free body diagram. Free body diagram of member AB. So now we have to take moment about point B. Moment about point B. So taking moment about point B. Moment about point B. So we know that n moments always left side anti-clockwise direction and right side clockwise direction. Now we are formulating the general equation. For the general equation derivation, we have to assume this moment and this moment also clockwise direction. Okay, so taking moment about point B. So this is the point B. So this is, we can name it as VA. So VA into, there is no perpendicular distance 0 only. Now HA. So HA, it is producing anticlockwise moment. So HA, the perpendicular distance between this point to this point is H1. This is H1. Now coming to MAB, so this is producing clockwise moment, so plus MAB. So now coming to this horizontal load, taking moment about point B, this is producing anticlockwise moment, so minus P, the perpendicular distance between this point to this point is H. Okay, so next one here. One more moment is that this is acting clockwise direction, so plus MBA. If you take this HD also, there is no perpendicular distance because it is acting at the point, so 0 value only. So this will be equal to 0. Summation of moment at point equal to 0. So now we can find out the HA. So HA equal to MAB plus MBA. These are all the end moments minus P into H divided by total height of the column, that is H1. Okay, this is equation number 1. This is equation number 1, HA. Okay, HA equal to MAB plus, this is end moment, MAB plus MBA minus P into H divided by entire height of the column. So now this is CD. Okay, so here the second vertical member, right side vertical member. So here UDL load is acting H2. Okay, so same free body diagram we have to draw because this end is fixed end, so horizontal reaction will be there, and here HC. Okay, this vertical reaction is VD. So again clockwise direction, because we are formulating the general equation, so we have to assume all the moments are acting clockwise direction only. So here MDC and MCD. So MDC means end moments at D of the member DC. CD means end moment at C of the member CD. Okay, so now taking moment about point C, that is summation of moment about point C equal to 0. We have to take moment about this point. So again same thing, HD. So here, so this is the section. This is the section we are taking moment about this point. Okay, so left side is section, this is right side. So for this case, anti-clockwise is positive and clockwise is negative. Okay, if this section is here, okay, this is XX. Okay, all the loads are behind the section. So for this type of section, anti-clockwise, okay, anti-clockwise moment considered as a positive sign, and clockwise negative sign. Okay, so now coming to here, so HD, it is producing clockwise, so minus sign, minus HD into the perpendicular distance is H2. So next one, clockwise moment is acting at a point D is acting clockwise, so clockwise is, so HD is anti-clockwise. Okay, anti-clockwise means positive, clockwise means negative. So MDC. Now coming to here, so this load, okay, so this load producing clockwise moment only. So clockwise means minus sign, so W into H2 into H2 divided by 2 because this is UDL. So now coming to here, MCD. MCD is clockwise, so minus MCD. This will be equal to 0. So now find out HD. HD equal to MDC plus MCD, then plus WH2 square divided by 2 divided by H2. This is equation number 2. This is equation number 2. So now we have to use third equilibrium equation, that is summation of all horizontal force equal to 0. Sum of all horizontal force equal to 0. Okay. So this is the given frame. Okay. This is the given frame. This is P. Here UDL load is acting W. Then entire height is H1, this is H2, this is H. So here horizontal reaction is there and here HD is there. Because we are using summation of horizontal force equal to 0. So no need to consider that vertical force and as well as moment also. So now while seeing this figure, 3 or 4 horizontal forces are there. One is HA, another one is HD, another one is P, and here W. So this direction is positive, this direction is negative. Sign convention. Okay. So now coming to here, HA positive. Okay. This is also positive plus P. Okay. And this is also positive plus HD. Okay. Then here. So this W is acting this side towards the left side. So negative sign minus W into H2. So this will be equal to 0. So already in the previous step we have determined HA as well as HD. So substitute equation number 1 and 2 here. We can find out the shear equation. We can find out the shear equation. So HA equal to, that is MAB plus MBA minus PH divided by H1. This is HA. So now we will write HD. Second, this one we will write HD equal to plus HD equal to MCD plus MDC plus WH2 square divided by 2 divided by H2. So now plus we will write this one P and this one also minus WH2 equal to 0. So this equation is called as shear equation. Shear equation. While seeing the rigid jointed frame, we can easily write down the shear equation. So see here. So here end moment is MAB. Here end moment is MBD. Only we have to consider the vertical column only. So this one only. Okay. So here MAB, MBA. Now taking moment about this point. So minus P into H divided by entire height of the column. Now coming to here also. Here MCD, MDC taking moment about this point. W into H2 square divided by 2. So next one, here one horizontal force is there, that is P. This is acting towards left, so minus W into H2. So that's all. So this equation is called as shear equation. So now case 2. So without derivation we can easily write the shear equation. So W H1 H2. So this is A, B, C, D. So we can write the shear equation without derivation. The first one is, we have to consider this vertical column. We have to write down the end moments. So here MAB. This end moment MBA minus. So taking moment about B. So W into H1 divided by 2. W into H1 square divided by 2 divided by this entire length of the column H1. This is for the first column. Now coming to the second, this member, okay, write down the end moments. So here the end moment is MCD. Here the moment is MDC. On the second vertical column there is no load. Okay, so this portion won't come. Okay, so divide by the entire height of the column is H2. So now we have to add the horizontal force here. So here towards right means positive sign. So W into H1 plus W into H1. So in this column there is no load. So here there is no term. This will be equal to 0. So this is the shear equation for this frame. Shear equation for this frame. Next one. This is another different type of frame. Here lateral load is acting. Load is H1, height is H1. Here the height is H2. So we can write the shear equation by seeing this figure. So first one, the end moments of the first column, that is MAB plus MBA. Here there is no horizontal load. Here horizontal load is there, but it is acting at the joint. If you take the moment also, here 0 only. So divide by the entire height of the column is H1. Now coming to this member, write down the end moments first. MCD plus MDC divided by H2. Here also there is no load. Okay. So plus summation of all horizontal load. So here only one force is acting, only one horizontal load is acting towards the right side. So positive sign. Plus P equal to 0. So this is the shear equation. So next one, instead, okay. So instead of fixed end, if it is hinged, okay. So instead of fixed end, see here, instead of fixed end, if any hinged support is there, for the same case, at the hinged support there is no movement. So this term won't come, MDC won't come. So remaining is same. So MAB plus MBA divided by H1 plus MCD. MDC, here there is no moment. MDC here, moment at joint D of the member DC. At the hinged support there is no moment. So this term won't come here. Divided by H2 plus P equal to 0. So this is the shear equation of this frame. I think we know about how to formulate how to derive the shear equation and how to write down the shear equation without derivation also. So now we will see how to analyze the rigid jointed frame by slope deflection method. The question is analyze the frame as shown in figure by slope deflection method and draw the bending moment diagram.